Picture a science lab in your head. Just any science lab. What kind of stuff is in there?
Odds are, one of the first things that comes to mind is glassware. Test tubes, beakers, bubbling flasks of mystery liquids, that sort of thing.
It's nearly impossible to imagine science without glass. In fact, you could argue that glassware is one of the iconic images of science. From the most basic science to the ultra-complex research happening at our national labs, sophisticated glassware is needed to make big breakthroughs happen. Take Argonne National Laboratory, for example. It's a busy hub of science and engineering just outside of Chicago that collaborates with dozens of other research organizations on everything from chemistry to high-energy physics to biology.
Say you're a scientist at Argonne. Your specialty is high-energy physics, and you're working on a new experiment that needs a special vacuum-sealed chamber. Problem is, the chamber you need doesn't exist. You've sifted through page after page of laboratory supply catalogs and no dice. So what do? Well, you talk to these guys.
Hi, this is Joe Greger. I work at Argonne National Laboratory. I've been a scientific glassblower for 52 years, and I've been employed at Argonne National Laboratory for 38 years.
My name is Kevin Moeller. I'm a scientific glassblower here at Argonne National Laboratory. I've been a glassblower for roughly about 10-12 years. I've been at Argonne for about 2.5 years.
You heard right. Joe and Kevin are glassblowers, and they specialize in creating the kind of custom laboratory glassware that makes Argonne research possible. Lots of it, anyway. Our former producer, Allison Lantero, gave them a call earlier this year.
First of all, we're going to get real simple. What is glassblowing?
Boy, you said simple.
No.
Wow. Well, at Argonne, we have lots of chemists, physicists, material scientists that all do experiments, and they need apparatus to do experiments in, and one of the top materials for doing chemical reactions is glass, simply because it is inert to almost all chemicals and reagents. So basically, the glass blowing we do is we take what we call preforms and we reshape them. We design and then build apparatus that works for the scientists in their experiments.
Both of them have deep family roots in the craft. Kevin's family has been in the glassblowing industry for 3 generations. As for Joe,
I'm actually a 4th generation scientific glassblower. My family had its own business for over 100 years, located in Milwaukee, Wisconsin. I started there at the ripe age of 17 after graduating high school.
Did you always know you wanted to be a glassblower?
I was never going to be a glassblower.
What were you going to be?
I had aspirations of being a professional golfer, and my dad asked me to come in for a year to help out, and that was 52 years ago.
As scientific glassblowers, Joe and Kevin work with preformed glass tubes, rods, and flasks, reshaping and combining them in intricate ways. That's in contrast to the blobs of molten glass you might have seen in an artistic glassblowing studio, but it doesn't mean their work is any less creative.
What does a typical day for you guys look like, or is there a typical day?
We turn the lights on every day. That's the same.
We use hand torches and lathes every day, but the work is different every day, and that's one of the best parts about the job. It's not come in and make 100 of these pieces every day. We're kind of puzzle makers where a client will come in and they've got an idea in their head, and we have to pull it out of their head and be able to make it for them. Keeps you on your toes, keeps you thinking every day. It definitely keeps it interesting.
Joe and Kevin aren't making pieces that are going to sit in a display case. After their creations have cooled, they get subjected to conditions that would obliterate your average decorative vase.
I always tell people that the scientists take my hand-blown apparatus and then they take it to their lab and torture it. They will pressurize it, they'll pump a vacuum on it, negative pressure, they'll freeze it with liquid nitrogen, they'll heat it, they can have reactions inside that are exothermic and generate a lot of heat. And if there's flaws or poorly manufactured product, that could be a weak point and could be a disaster inside a lab during an experiment.
So here they are, using techniques that have been around for thousands of years to craft components for some of Argonne's most advanced scientific research.
Sometimes the projects can be incredibly demanding. Joe said there's been a trend towards smaller, more intricate glasswork, like miniature reaction chambers and tiny optical windows for high-powered lasers.
A job I'm just finishing up on now was very complicated. It was very stressful, trying to fit an awful lot of different angles and tubes into a small space and not have it break. That's one of the things about glass. You can do a lot with it, but if you don't know what you're doing, it'll crack and then you have to start over. We actually have to be familiar with over 150 different glasses, and glasses have to be compatible to seal together. And if they don't have the what we call COE, coefficient of expansion match, when they cool, they're going to pull apart and break. So there's a lot of science that we have to know to be able to get to the finished product that the scientist is looking for.
It's complex, precise work that draws on their deep experience, technical savvy, and an ability to understand the individual needs of researchers across Argonne's vast range of scientific fields. But when it all comes together, Kevin said, the results can be incredibly rewarding.
There's really, almost nothing more satisfying than finishing this one-of-a-kind custom piece of glassware, and you're looking at it, and you're sitting there saying, you know what, I made that, I created that with my own two hands, and in a lot of cases, you can sit there and say, nobody else, in the country, in the world, has ever made this exact piece. And in working in a research environment like this, who knows what that glassware is going to create further down the line? Is somebody going to discover something or create something using your glassware? Well, that's a big part of it.
In my mind, this is probably one of the top 2 or 3 premier glassblowing positions that a glassblower like us could have. The projects we get on, the science that they're doing here, I'll say for the greater good, we're trying to help humanity in all areas of life, cancer research, water purification. Boy, you can just make a list of everything that you hear on the news, and we're working with it. Everyone has frustrations in their life, but as far as glassblowing, I can't remember a day that I didn't want to go to work. I just love it.
This episode of Direct Current is dedicated to the makers at the Department of Energy, from the low-tech to the high-tech.
People like Kevin, Joe, and all the other scientific glassblowers at our national labs who are using classical techniques to create the tools for cutting-edge science, and people like the researchers who are pioneering technologies that could define the next generation of manufacturing. I'm Matt Dozier.
And I'm Court Creer. Coming up after the break, we'll introduce you to some folks who are reimagining the way we make, well, everything. Stick around.
We have a podcast about energy.
The jewels that these national labs are.
In terms of science and scientific capabilities.
Big dreams can happen.
Keeping our nation safe.
Clean energy is wave of the future. It's
America's economic engine.
It's science.
For the people.
This is Direct Current.
We turn now from the 2,000-year-old art of glassblowing to another technology to make stuff, one that's still in its infancy.
That technology is additive manufacturing, aka 3D printing. You've almost certainly heard about it in the news by now. Maybe you've even seen a 3D printer in action, turning a computer sketch into a real physical object.
There's a lot of hype around 3D printing. Advocates of the technology say it could transform society and lead to a new industrial revolution. And a huge hobbyist community has sprung up around it, with websites full of blueprints for printing basically anything you can dream up, from rotisserie marshmallow roasters to desktop skeleton models.
We're going to get into all of that. But first, let's go over some of the basics. What exactly is 3D printing, and how does it work? To help, we brought in an expert from the Energy Department's Oak Ridge National Laboratory in Tennessee, a place that's on the cutting edge of 3D printing science.
My name is Amy Elliott. I'm a research scientist here at Oak Ridge National Lab.
Amy's path to Oak Ridge began at a young age when she got really into robots.
So I actually started in engineering doing robotics. I thought robots were really cool, did the high school robotics competition. And when I got to grad school, it was highly competitive, so it was very difficult to get into robotics research.
As she was struggling to break into the field, she learned about this relatively young technology called additive manufacturing. And it just kind of clicked.
I realized, hey, these 3D printers or these additive manufacturing pieces of equipment, they're just robots that make me something. So I kind of went at it from that angle and haven't looked back since.
3D printing became a springboard for Amy's career. She went on to get her PhD in Additive Manufacturing and joined the Oak Ridge team in 2013 as 3D printing really started to explode in popularity. Side note, we're going to be using the terms 3D printing and additive manufacturing interchangeably throughout this episode. Whatever you want to call it, we asked Amy to break down how it works.
3D printing is not like traditional manufacturing. With traditional manufacturing, you're actually taking a block of something and you're carving it down. We call that subtractive manufacturing. So there's a lot of waste associated with that. There's a lot of energy that was spent making that block, and then you also have to spend energy carving away at that block, and then you have to spend energy recycling those chips that you just made. So with additive, instead of carving, we're adding material, hence the name. So pretty much all of this processes work in a layer-wise fashion. So you decide the shape that you want, you digitally slice it into layers, and the machine will make each of those layers one at a time from bottom to top.
There's a bunch of ways 3D printers can create those layers. Amy said there are actually 7 different additive manufacturing techniques, and they can print using everything from plastic to metal to ceramics, even bamboo.
Probably the most well-known is called extrusion, where it's kind of like a hot glue gun. You have a plastic that melts when it's pushed through a hot nozzle. And then you take that nozzle and you draw something with it. You draw that layer. So if I were to draw a square with a hot glue gun and I'll let it cool, and then I'll draw another square on top. And if I kept drawing squares, I'd eventually to have a 3-dimensional cube.
So the basic principle is really simple, but it's also kind of incredible, watching intricate designs take shape layer by layer right before your eyes.
It's kind of like if you hear your paper printer moving back and forth, it's like this noise, like it'll do that. And it pretty much just does that for hours and hours and hours until the part comes out. So it's kind of sci-fi when you think about it. The first time I saw one of these printers running, I literally watched the whole 2-hour print. I was just so mesmerized. I actually have 4 desktop printers in my basement right now in various forms of working and not working. My husband has a bunch of motorcycles that he wrenches on, so that's his hobby. And I have 3D printers, so it's kind of the same thing. I like to soup them up. I like to see what I can print. I like to tune them. I like to make presents for people. Actually, right now I'm building a meter-cubed build volume printer. Hopefully I can get that going, but I want to print, maybe some fabric, make some 3D printed clothes, that kind of thing. I don't know. I just want to print all kinds of stuff.
Amy's not the only one at Oak Ridge who's been captivated by 3D printing. Lonnie Love, a corporate fellow at the lab, remembers the day he first saw one in action.
A good friend of mine, Craig Blue, he's a program manager at the lab, came to me, and my group had been doing some 3D printing with plastic printers, and he said, I need you to look at this new printer we got. It was more for materials research than anything. And he showed me some parts that were coming out of it. And I'll never forget telling him, I was like, either my office is going to move next to that machine, or we're going to move that machine next to my office.
That was about a decade ago. Today, Lonnie leads various 3D printing projects at the Manufacturing Demonstration Facility, or MDF, which is supported and managed by the Energy Department's Advanced Manufacturing Office. Created in 2011, it's the federal government's first research facility devoted to connecting businesses with advanced 3D printing technologies. The MDF is the lab's home for researchers like Amy, who are pushing the boundaries of 3D printing in a bunch of exciting ways.
Shortly after getting his hands on that 3D printer, Lonnie and his team used it to print a hand. In just 1 week, they were able to design, print, and assemble a hydraulic-powered robot hand, which got a lot of media attention.
So that was really the spark that really took off in terms of Oak Ridge looking at additive. We'd been dabbling with it a little bit, but we started to realize pretty quickly there was still a lot of scientific challenges and a lot of things that Oak Ridge could really do to help push the technology forward.
The earliest 3D printers were small and really slow. That's fine if you just want to print a pencil holder here and a novelty paperweight there, but it's not going to cut it for bigger jobs, let alone manufacturing on an industrial scale.
They made things that were about a cubic foot in volume. You could make something big at that point in time was something the size of a milk jug. They were very slow. It would take you a week to make that milk jug. And the materials were expensive. That milk jug would cost you thousands, if not tens of thousands of dollars to manufacture. And so we started looking at what are things we can do to go much larger, much faster, and much less expensive.
So researchers at the lab set about designing larger, faster machines that could print in a wider range of materials. And it wasn't long before they started tackling even more ambitious projects.
Local Motors was a small automotive startup company. They came in, and their CEO, Jay Rogers, was watching what we were doing, and he goes, "Hey, do you think you could 3D print a car?" And I was like, sure, why not? It sounds like a good challenge.
Here's the catch. They needed to have the car ready in just 8 months, in time to print it in front of 100,000 people at one of the biggest manufacturing trade shows in the world.
So everybody really pulled together real tight and started working extremely hard. And the first time we tried to print the car, it was a complete disaster. We were going at about 10 pounds an hour, which is 2 orders of magnitude faster than anything else we'd ever done. But the car, as we're printing it, it started to crack. It started to peel apart like a stack of cards.
This was in 2014, before anyone had really tried to print something this size. They had to design the 3D model of the car, build new 3D printing hardware, develop new materials, and troubleshoot problems when things fell apart.
Lonnie said the team was still making adjustments to the entire process up until just 2 days before the show. During the event, the body of the car took shape over 44 hours of printing. Then Local Motors assembled the rest of the components on site. And on September 13th, 2014, the world's first 3D printed car rolled out of McCormick Place in Chicago.
There's an element of chaos in these moonshot projects, as Lonnie calls them, and that's on purpose.
Failure, to me, is a stepping stone to success. If you're not pushing yourselves, if you're not delving into the unknown, you're never really pushing the technology forward. You should embrace those failures as opportunities.
Pushing those boundaries paid off big, in the form of a giant specialized 3D printer capable of churning out car-sized projects in record time.
We call it Big Area Additive Manufacturing, BAM. BAM technology is essentially large 3D printing.
That's Rick Neff. Rick works for Cincinnati Incorporated, the company that partnered with Oak Ridge National Lab to develop the BAM. And while this technology is relatively young, Rick's company has been around a long time.
We were founded in 1898, so a little bit later on this year we'll be 120 years old. We've been owned by the same family since we were founded.
One of the things Cincinnati specializes in is these big computer-guided machines that cut sheets of material with lasers. They combined that technology with Oak Ridge's 3D printing expertise to create something bigger than anything on the market. A lot bigger.
At the time, the biggest 3D printer available was a box, about 3 feet by 3 feet by 2 feet. The largest BAM model in comparison is 8 feet wide, 20 feet long, and 6 feet tall. That's more than 50 times the volume.
We went from printing something the size of a big wheel for a kid to something the size of a full-size car.
Oak Ridge National Lab is all about partnerships like this one. Companies and research institutions from all over the world come to the MDF to collaborate on finding better, cheaper, faster ways to make stuff.
Part of the whole idea of the manufacturing demonstration facility is to try and help business be more competitive. Working with the lab was really cool, but one of the other things that we really found out is that it's not just working with the lab. Part of the MDF is that they have so many companies that have come in that are working with them to collaborate with them that we wind up collaborating with a whole bunch of other companies. In order to accelerate innovation, collaboration really helps out.
That kind of collaboration can lead to some pretty amazing breakthroughs, although not all of them are as flashy as a 3D printed car or robot hand. Here's Lonnie again.
I drive most of my team crazy because we do a lot of very innovative applications. Like we've printed a sub for Carter Rock Naval Warfare Center. We've printed cars, molds for boats and yachts and all kinds of neat stuff. But I tell people there's 3 killer applications for additive. Tooling, tooling, and tooling.
Generally speaking, when you want to manufacture parts for something, whether it's a car or a refrigerator or a wind turbine blade, you need a mold. You take your material, press it into the mold, remove the part, then repeat. Over and over and over.
It's really the foundation of manufacturing. When you look at automotive, you look at appliances, you look at aerospace industry, they're shaping parts that go on planes and cars and refrigerators. They're shaping them by pushing the material against a mold. So you can't make a refrigerator without tooling. You can't make a car without tooling. And we've seen a slow erosion of that industry in the United States.
But molds are really slow and costly to make. Each one is custom designed and then carved out of a block of solid material. That's the traditional subtractive manufacturing approach Amy was talking about earlier, and it creates a ton of waste.
Additive manufacturing, on the other hand, is really good at making the kind of one-time, unique creations with super exact specifications that machine tools require. And that could make it a game changer for an industry that has seen some hard times in the U.S.
Americans have always been really good at making things. We are a country of builders, doers, and makers, and that's a really exciting thing in the global economy. We've got some of the smartest people, some of the hardest working people in America, and all the things that we've offshored in the past, a lot of those things can still be made here, and can be made here by using technology. We worry about technology taking away jobs in the United States. Really, technology is what keeps us competitive in what we do.
Both Lonnie and Rick see a bright future for manufacturing in the U.S., but there's more to this future than simply cutting costs by using new tools.
We're talking about a radical shift in the entire engineering process, led by the next generation of thinkers who grew up with 3D printing at their disposal.
My name's Sarah Palmer. I am a rising senior at Worcester Polytechnic Institute, majoring in robotics engineering and minoring in mechanical engineering.
My name is Rowan Palmer. I am a rising sophomore at Yale University, and I am majoring in mechanical engineering.
Sierra and Rowan are sisters. They're a few years apart, and they both got into engineering in high school through this big international robotics competition.
Yeah, so I heard about the first robotics competition because it was taking place at the high school that Rowan and I both ended up going to. And I was like, I'll go to the interest meeting and just see what I think. And I remember just going and being like, wow, this is so cool. Like, I can be like super creative and stuff. And I met a group of mentors that were super passionate about it, as well as other students.
Rowan joined the school's team as a freshman a couple of years later. But while her sister dove into building and driving the robots, she started out documenting the competition as the team's photographer and videographer.
And then after 2 years on the team, I was like, wow, I actually prefer the robot mechanical stuff. And I found my love for robotics and STEM and engineering when I was taking pictures of it. And I realized I wanted to do the stuff that I was taking pictures of. And so that was kind of a cool transition for me because I'd always known I liked math and science and I was into art. But like seeing it in front of my face, I was like, oh my gosh, this is actually something that brings all of those things together.
Rowan explained how the first robotics competitions work, and it's pretty intense.
So they announce the game, you figure out what the things you have to do are, so how you score points, what the end goal, and then you have 6 weeks to build our robot with your team to play that game. And at the end of 6 weeks, you have to bag up the robot, you have to be done. And then whenever you get to a competition, you can take it out of the bag, work on it, and then you compete multiple rounds in a row, and then it's a tournament, and whoever comes out on top.
I'm sure 6 weeks didn't feel like a whole lot of time to build a robot from scratch, right?
No, it was definitely a lot.
Yeah, it was definitely a big time commitment. I mean, the team met about 3 hours a night, 5 days a week during the entire build season.
And Saturdays, 9 to 5.
Oh, yeah, and like all day Saturday.
Rowan and I were both competitive athletes too, but it was also super worth it in the end to be able to do something like that.
The competition involves students of all skill levels, but with such a heavy workload, it can be tough to get up to speed. So teams get matched up with mentors who help advise them on their projects. Enter Lonnie.
So about 2010, 2011, again, I mentioned Craig Blue earlier. He's kind of my partner in crime. He and I started mentoring for a couple of local schools, the first robotics program. And I'll never forget, I go into the school the first night and, we got 6 weeks to build a robot. And someone like, okay, well, where's your machine shop? And the kids were like, well, we don't have a shop. And I'm like, oh my God, this is a disaster. I'm going to spend thousands of dollars on band saws and drill presses and this, that, and the other. And this kid comes up and goes, well, we do have a 3D printer. And I was like, you got to be kidding me. It was a new school, and for startup funds, they had bought a Stratasys U-Print 3D printer. And I was like, okay, this is going to work. And so I sat down and taught 5 kids how to do CAD. And about that first year, about 20% of their robot was printed. And they got it. They took to it like fish to water.
The next year, Oak Ridge opened up the MDF to the high schoolers, giving them virtually unlimited access to the lab suite of high-tech 3D printers.
Whatever anybody wanted, we printed it. And we just saw this massive explosion of creativity from these kids by letting them be able to design freeform. They were unencumbered by reality. They didn't know what they couldn't do. So with traditional manufacturing, you have all kinds of constraints. These kids, they didn't know what those constraints were, and so they were designing things that were really creative.
Sierra's class was one of the first to get to explore the lab's incredible playground of next-generation manufacturing equipment.
My freshman year was when we actually started working at the manufacturing demonstration facility at Oak Ridge National Lab. So it was cool because we were kind of that inaugural team to kind of go in and be like, okay, so we have all of this stuff. What are we going to do with it?
They put the new equipment and insight from Oak Ridge to good use, winning numerous regional titles and even reaching the World Championships. In 2014, the team set another milestone, creating the competition's first 3D printed robot.
Did 3D printing kind of change what you could see was possible?
I think it did. I had to design something where I had to use just standard manufacturing. And I remember going from designing for 3D printing to designing for that and feeling like I was so restricted in a way because I couldn't do like these smooth curves or things like that.
Agreed. I definitely think that having the 3D printing adds an element of, because you're less restricted, you can make things that function the way you want them to and also be very beautiful. And I think that's something that's really nice.
This summer, both Sierra and Rowan are back at Oak Ridge National Lab as interns, putting their robot battling backgrounds to work on research that's advancing the state of the art.
I think that's like one of the coolest parts is seeing how the things that we did in robotics could directly translate to real scientific research and like real improvements in manufacturing and things like that, because there's a lot of times where they would see like, oh, your robot survived on a playing field for 2 competitions or 3 competitions. Maybe we could build other stuff out of that and it would also survive.
When it comes down to it, this is what the Energy Department and National Labs do best. They push forward technologies with real potential to change the world for the better, and they make connections.
Connections with scientists and educators, with entrepreneurs and engineers, and with the young people who will find ways to use these technologies that we couldn't possibly imagine.
I think we're just at the start of something that I think in the next 20 to 30 years is going to completely change society for the better. Not because so much that they're going to be 3D printing everything, but we really are getting kids interested in making stuff again. I think what we're seeing is a birth of a whole new generation of makers that are going to really transform society. To me, the future is extremely bright.
That's our show. Before we wrap up, I want to mention that we barely scratched the surface in this episode when it comes to the work that makers are doing all across the Energy Department and our national labs.
So head over to our website where we've got lots of videos of scientific glassblowing and huge 3D printers in action, as well as tons more information about amazing technologies that are changing the way we make stuff. Also, we love hearing from our listeners, so email us at directcurrent@hq.doe.gov or tweet @energy if you've got questions or just want to say hello.
Quick shout out to Daniela. She's a high schooler from Venezuela who sent us a really nice note recently. If you're enjoying the show, why not share it with a friend or leave us a review on iTunes?
Many thanks to Joe Greger, Kevin Mahler, and Justin Bro at Argonne National Lab.
And at Oak Ridge National Lab, thank you to Amy Elliott, Lonnie Love, and Jenny Woodbury. Thanks as well to Rick Neff, Sierra Palmer, and Rowan Palmer.
Direct Current is produced by Matt Dozier, Paul Lester, and me, Court Creer. I also create the original artwork for every episode, which you can find on our website.
Additional support from Ernie Ambrose, Gigi Frias, and Atik Waraish. Special thanks to our intern, Quinn Dang. We're a production of the U.S. Department of Energy and published from our nation's capital in Washington, D.C.
Thanks for listening.